Greetings everybody, and welcome back to my series on probability and statistics. I am Dr. Lathram, and today we'll be talking about multivariate distributions and independence. So let's start off with a couple of definitions. Because we're in the multivariate case, we're going to have more than one random variable running around. So let's suppose that we have two random variables, y sub 1 and y sub 2. When they are discrete random variables, we define the joint probability density function, which is the joint Pdf for y sub 1 and y sub 2, to be little p of y sub 1, y sub 2, and that will be equal to the probability that capital Y sub 1 is equal to little y sub 1, and that capital Y sub 2 is equal to little y sub 2. And this is going to hold for all y sub 1 and y sub 2 in the plane. Coming over to the continuous case, for continuous random variable y sub 1 and y sub 2, we define the joint cumulative distribution function, so the joint CDF, to be the probability that capital Y sub 1 is going to be less than or equal to A, and that capital Y sub 2 is going to be less than or equal to B. Now, in the case that we've got a non-negative function, little f, and this little f allows us to write the cumulative distribution function as a double integral from minus infinity up to b and minus infinity up to a of little f of y sub 1 and y sub 2 dy sub 1 dy sub 2. Then we call this little f the joint probability density function for y sub 1 and y sub 2. So now let's look at some properties of these joint distributions. If y sub 1 and y sub 2 are random variables, then the joint CDF, capital F of a sub b, and for little f being the joint PDF, then if we look at the limit as a and b head off to negative infinity of the joint cumulative distribution function, then that will always end up being 0. And if in addition that we pick two numbers, a sub naught and b sub naught, as real numbers, then in the case that we hold b constant at b sub naught and then let a head off to negative infinity, we get 0. But also, if we hold a constant, so if we hold a constant at a naught and let b head off to negative infinity, we'll also get 0. Then finally, if we take the limit as a and b head off, both of them head off to infinity, then that will give us a limit of 1. For our next property, suppose that we have real numbers a sub 1 less than or equal to a sub 2 and b sub 1 less than or equal to b sub 2. Then if we wanted to write the probability that y sub 1 will be sandwiched between a sub 1 and a sub 2, and y sub 2 will be sandwiched in between b sub 1 and b sub 2, this will be represented by the integral from b sub 1 up to b sub 2 and a sub 1 up to a sub 2 of our probability density function f of y1, y2, dy1, dy2. Now this will end up evaluating as capital F of a sub 2 b sub 2 minus f of a sub 2 b sub 1 minus f of a sub 1 b sub 2 plus f of a sub 1 b sub 1. Now what is that expression really giving us? Well, what we see this expression really as being that for capital F of a sub 2 b sub 2 is really represented by integrating over this entire big rectangle that we have. So all the way over from minus infinity in both directions up to a sub 2 b sub 2. Now what we're going to do is subtract off a sub 2 b sub 1. Well, a sub 2 b sub 1 is going to be this ordered pair, and we're integrating there everything back along this horizontal line, so all of this red area is going to be represented by f of a sub 2 b sub 1. So we had this entire rectangle, and now we're taking off this red chunk, but then we'll also take off this other blue chunk. So this other blue chunk is represented by capital F of a sub 1 b sub 2. So now what we've done is we've taken off this chunk, we've taken off this chunk, but now this, we can see we have this area for a sub 1 and b sub 1 that shows up twice, that we took out that chunk twice. So how do we remedy that? We put that chunk back in, and that's what we're talking about when we're putting capital F of a sub 1 b sub 1 back in. And so this integral makes perfect sense as being this particular summation. So those properties may have been a little bit daunting to have to deal with, so let's actually take a concrete example and see how each one of those tends to play out. So what we will do, because we're dealing with graphing two variable functions, we'll go over to a computer algebra system. So we'll fire up Maxima, and we'll go to kind of our go-to family of distributions, our normal distributions. Now we'll talk about those a lot more in upcoming lectures. They'll play a really big role in probability and statistics. And so for now, if those seem a little bit unfamiliar, don't sweat it too much. We'll encounter those guys a whole lot more later. But for now, I will define this probability density function. So what I'm going to say is going to be a probability density function, little f of xy, and I'm going to define that as 1 over 2 pi times e to the negative x squared plus y squared over 2. Now, if I'm saying this is a probability density function, we need to kind of verify that a little bit. So two of our properties that we're interested in is, number one, is it going to be positive? Well, exponential functions are always going to be positive. I'm multiplying by 1 over 2 pi, that's positive. So my function f of xy is going to be a positive function. The second thing that we have to worry about is if we integrate, or if we sum over our entire sample space. So if we take the probability of our entire sample space, which in this case is going to be the entire xy plane, that we should have a value of 1. Well, let's do the integral and see if that actually turns out to be the case. So I want to integrate, but this is a two-dimensional PDF, so I need to do a double integral of my PDF, f of xy, and I want x to go from minus infinity to infinity, and then I also want y to go from minus infinity to infinity. And so if I perform that integration, let's see what Maxima will turn around and give us. Well, sure enough, we get a value of 1. So that's telling us that the volume underneath that particular surface is going to be 1. So let's see what the graph of that kind of surface is going to look like. We know, or we've talked about previously, that the Gaussian distributions are a family of bell-shaped functions. So let's see what this thing looks like. So if let's do a plot in 3 dimensions of f of xy, so the plot of our PDF, and we'll say that x is going to go from minus 5 to 5, and y going from minus 5 to 5. So if we graph that, let's see what the picture will look like. So Maxima gives us a graph, and we see that in this picture we have something that kind of looks like a bell-shaped curve, but actually it's a bell-shaped curve that's kind of more like a bell-shaped bump, that it's got this kind of symmetry to it all the way around. This thing just looks like a little bit of a mountain peak, that then tapers off in each direction. So it kind of looks like a bell-shaped curve if we were looking at it this way, but if we turn around and look at it this way, it also looks like a bell-shaped curve. So that's kind of characteristic of our normal family of distributions. We get surfaces that look like that. And so our last integration then showed that if we integrate from minus infinity to infinity in both directions, that the volume underneath that curve, underneath that surface, will actually be 1. So that yes, we do have a probability distribution defined in this way. So that's our PDF. Now let's take a look at our CDF. Okay, so for our CDF, that was the cumulative distribution function. So we define that as being the function capital F of AB, and it was the double integral. So we have to integrate over the y values, integrate over the x values of our density function f of xy, and we're having x go from minus infinity up to a, and we're having our y values go from minus infinity up to b. Okay, so those were our functions f of xy. So let's take a look and see what that picture might look like. So if we do a 3D plot, now, not of our PDF, but of our CDF of AB. So we're going A going from minus 5 to 5, B going from minus 5 to 5. Let's see what this graph looks like. And we get a curve, we get a surface that looks something like this. Now, talking about our limit properties that we were talking about before. So we've got the a-axis here on this side going off to negative infinity. So what those limits we're talking about, that if we head off to negative infinity, so we go off to negative infinity in this direction, that our cumulative distribution function tapers off and eventually decays down to 0. It doesn't matter whether we go off, if we pick a value for a naught, for a, and we head off along this line, that's going to head off to 0. If we pick a value for b and let a head off down to 0, then in either direction, however we're going, we're going to end up going down to have a limit of 0. Okay. Now, if we take the limit as a and b head up to positive infinity. So now we've got our cumulative distribution function. It's coming up doing this, and it's going to come up and really reach kind of this maximum value. And you can see this maximum value is going to be there at 1. So as we head off into the positive infinity direction this way, the positive infinity direction this way, that we get this kind of tapering up and leveling out, so that we get something that kind of looks like maybe a horizontal asymptote, or the surfaces is approaching up here to a value of 1. So this is really what we were getting at with those particular limits. As we head off in one direction, they go to 0. As we head off in another direction, they head up to 1. So now, just as was the case for our single variables, the relationship between the CDF and the PDF in the continuous case is given by derivatives. Well, in this case, it's driven by partial derivatives. So if y sub 1 and y sub 2 are random variables with continuous random variables, with CDF given by capital F and PDF given by little f, Then if we take the mixed partial, so the second mixed partial, that will give us, of the cumulative distribution function, that is our probability density function. So necessarily, why is that going to be the case? Well, if we just go from the definition of the CDF, if we take derivatives in both of those cases, derivative with respect to b, the derivative with respect to a, we are right back to our integrand. So kind of the fundamental theorem of calculus right back at us. So now let's look at another new definition. So what this new definition will do will allow us to go from the multivariate case down to the single variate case. So let's see how we can do that. Well, if we've got two random variables, y sub 1 and y sub 2, and that we have a joint PDF for those being little f of y sub 1 and y sub 2, then these things called marginal probability functions in the discrete case are defined as, so the marginal probability function for y sub 1 is going to be the sum over all possible y sub 2's of our joint PDF. The marginal probability function for y sub 2 is given by little f sub 2, y sub 2, and we get that by summing over all possible y sub 1's for our joint PDF. Likewise, in the continuous case, if we want the marginal probability function for y sub 1, so little f sub 1, y sub 1, then we will integrate from minus infinity to infinity, so we're integrating over all possible values of y sub 2 of our PDF. Likewise, if we want the marginal probability function for y sub 2, so f sub 2, y sub 2 is going to be the integral from minus infinity to infinity over all of the y sub 1's for our joint PDF. And so kind of the bottom line is, if we want to go from the multivariate case down to the single variate case, so each one of these marginal probability functions are single variable functions, we do that by essentially either summing or integrating over all the other possible values for the other variables that we may have in our distributions. So this allows us to go from the multivariate case down to the single variate case. So now let's talk about conditional PDFs. So again, we've got y sub 1 and y sub 2 being random variables, with our joint PDF being little f of y sub 1, y sub 2. In addition, we'll assume that our marginal PDF for y sub 1 is given by little f sub 1, and our marginal PDF for y sub 2 is given by f sub 2. Then the conditional PDF of y sub 1 given y sub 2 is going to be defined as f of y sub 1 vertical bar y sub 2, so it's like we're assuming that y sub 2 is given. Then that's going to be defined as the joint PDF for y sub 1 and y sub 2 divided by the marginal PDF for y sub 2. So we're holding y sub 1 constant, or we're holding y sub 2. We're assuming that y sub 2 is given, and we're allowing y sub 1 to vary. So we're assuming that y sub 2 is given, and so we have what in essence kind of looks like our conditional probability. We've got the probability for both divided by the probability for the thing that we're given. And likewise, for the conditional PDF of y sub 2 given y sub 1, now we are given y sub 1. And so how does the definition change? Well, we got our joint PDF, so our PDF for y sub 1 and y sub 2, and then we divide by the probability function, so the probability function for y sub 1, so the one that we're actually assuming that we are given. But then we can likewise define conditional CDFs. So we have y sub 1 and y sub 2 being jointly continuous random variables with joint density function, little f. Then the conditional distribution function of y sub 1 given y sub 2 is equal to little y sub 2. Then that's capital F of y sub 1, vertical bar again, so we're assuming that y sub 2 is given. And that's going to be the probability that y sub 1, capital Y sub 1, is less than or equal to little y sub 1, given that we are fixing a value for y sub 2 at little y sub 2. And the conditional distribution function of y sub 2, given that what capital Y sub 1 is equal to little y sub 1, is likewise going to be the probability that y sub 2 is less than or equal to y sub 2, little y sub 2, and we are fixing a value of y sub 1. Now, kind of coming back to our surface ideas, what we're actually doing in each one of these cases is we're doing an integral. But we're doing an integral in the first case for y sub 1 given that y sub 2, we're doing an integral that will be kind of parallel to the y sub 1 axis. We're fixing a value of y sub 2, and then we are doing an integral from minus infinity up to y sub 1 for that particular slice that's parallel to the y sub 1 axis. And likewise, if we're doing the conditional distribution function of y sub 2, it's like we're doing integral on the y sub 2 axis, but the y sub 2 axis, we're taking the slice that's going to be at where capital Y sub 1 is equal to little y sub 1. So we're doing in the single integrations, which will end up being a function of y sub 1, and this one will be a function of or rather this top one will be a function of y sub 1 because we're holding y sub 2 constant, and for the second one it'll be a function of y sub 2 because we're holding capital Y sub 1 constant. Now we're ready to encounter our first definition of independence. So independence should not be confused with mutually exclusive. They're really two very different concepts. Mutually exclusive, meaning that one can't happen when the other happens, that their intersections are going to be empty. For independence, we've got something very different. So if y sub 1 and y sub 2 are random variables with joint Pdf little f, then we've got marginal for y sub 1 being little f sub 1, the marginal distribution for y sub 2 being f sub 2, and y sub 1 and y sub 2 are independent if and only if the joint probability density function is equal to the product of the marginal distribution functions. Now, what we also have for that is that if y sub 1 and y sub 2 are as above, then y sub 1 and y sub 2 are independent if and only if the conditional probability functions, the conditional probability densities that we talked about, y sub 1 given y sub 2 is really just the marginal distribution for y sub 1. So this is really saying that if we pick a value for y sub 2, it doesn't really matter what value we pick for y sub 2, we're still going to get the same function back. And so the value, the density for y sub 1 is going to be independent of the value of y that we chose for y sub 2. Likewise, if we hold y sub 1 constant, it doesn't really matter what value we choose. The conditional probability is just going to be equal to that marginal probability function. Now, why is that really going to be the case? Well, the proof for that follows immediately from the definition. So if you go back and write down the definition for the conditional probability and then the marginal probability, you'll see that yes, sure enough, that will give you an if and only if, and it follows immediately.